The GPU part is now taken care of. Now we're going to the more classic aspect of MPI and scenario you may have seen. And there's one which is not very hard. I've seen many, many times, which is when you have to deal with a message, you have to receive a message, but you don't know the length of this message. And I've been surprised to see that typically what happens is we send the length and then we send the data. The arrow is in the wrong way. It's from left to right. That will be O1 or O2. So it means that you send effectively two messages. So from left to right, the sender sends the length, and then the sender sends the data, not the other way around. So it means that you're paying twice the latency, which, remember, typically is not something we like to pay. Latency, extra synchronization, and so on. It's not really something you would like to do in program, especially if you have many messages to send. So to avoid doing that, we just need to discover there's something when we send messages, which I briefly mentioned this morning about the status when I said tag and source. It's something called an envelope. Every time you send a message, something called an envelope is created along with it. It's like when you send a letter by mail, you put your actual letter in an envelope, but on the envelope, there's the address of the recipient. There's the stamp. There's the address of the sender if we need to send it back. It's the same thing here. So it's a source of information that can be used to then somehow recalculate the size of the message. Have you seen this morning? If you were here this morning, you've seen it. If not, you may have seen. In MPI receive, there's an argument called the status. Okay? From the status, we can retrieve the count. So let's see how we can do this. Because you may say, yeah, but to get the status in MPI receive, we must call MPI receive. But the problem is we cannot call MPI receive because we don't know the length yet. So this is what we're going to do. We're going to call this function called MPI probe. So what MPI probe does is that it goes in the queue. Remember this morning I was talking about the queue of the messages around? They just are in the queue that you're going to go through and you call MPI receive, the first one to match. MPI is going to check in the queue without taking the message. So it will just go and check the envelope of the message. It's like you receiving a letter, just checking the letter, but without opening it. So it's just going to do that and say, okay, so in this message we have a message coming from that rank or that MPI process with that tag, that communicator, and the status for additional, other variant. You're going to probe the message coming from that source with that tag in that communicator, and the information retrieved will be put in that status. Okay, and then from there we'll see how to get the count in a second. First, let's have a look at the bindings. So in C, nothing new here. The source, so the sender's rank and the tag are both integers, and the communicator MPI com status MPI status. Now, Fortran, same thing. Integer MPI com MPI status. Okay. Now this is where the fun begins. Just from this status, you have another function, called MPI get count, which is the one where you pass your status and you get the data type and the count. Okay, so this is how you can retrieve that count that we're after. So you see nothing new here. The types you already know them. Fortran, same thing. So this allows you to send a message once without even having to tell the recipient the size of your message. Okay, the recipient can find it directly. So you save this extra message. Again, even in code developed by HPC people, it's pretty far from uncommon to see these two messages. And if it's inside the loop, even if you don't pay the latency, it's not a big thing. if it's inside a loop of a message you send a few million times, you can save a few million messages, which means your latency is longer paid, well, it's paid a few million times less, and the amount of data transiting over the network now has, say, 1 million times whatever it is you were sending. The less time you spend on the network, the more time you spend on the CPUs. And the CPUs are much faster than the network. So it's all connected. Before going to the exercise, there's something I wanted to mention, which are the protocols. Because behind the scenes, here we are standing at the MPI level, but behind the scenes, at some point somewhere, data has to be moved over the network. And there are many ways to do it, many protocols. I will mention just two very quickly. Eager and rendezvous. Eager is when the data is sent along the envelope. So I want to send 4 integers. So I call my MPI send, I pass my buffer for MPI end, okay? MPI behind the scenes creates a little envelope describing what's in it, 4 MPI integers coming from this MPI process to this MPI process to this tag and so on. Sends the envelope, but if it uses the eager protocol, it also puts the data right with it, okay? And it will store it on the recipient. You may say, where? Where is it going to store it? The recipient hasn't called MPI receive yet. Well, what happens is every MPI process has a little buffer that it allocates for this, typically a few megabytes. For tiny messages that we know are not going to be a problem, when you send 1 MPI end, so 1 integer, so 4 bytes, we know you are extremely unlikely to result in a memory, in an out-of-memory failure on the recipient. You can take 4 bytes. So you send the 4 bytes with it. The rendezvous, however, is totally different. Rendezvous is you send the envelope, but you keep the data. You keep the data for now. Only when the recipient tells you, send the data, that you send the data. So you're going to see the advantage of it. You can switch between the two by setting an environment variable or something to whatever threshold will define which protocol you have to use. So depending on the implementation, you have this variable, or these variable, or these variable, or these variable. So these variables. So it's you have to check the documentation. Unfortunately, at least at the time of speaking, we don't have a unified, universal, common, standardized way to set the value of the eager threshold. So far, it's still one per implementation. Remember then, that's a good method we're going to link back to MPI and MP. You see how instantly it becomes far less interesting when just to set one environment, one tiny threshold, you have 4 different ways to do it. Now imagine that before MPI or OpenMP were created, this was happening for every single thing. You didn't have 1 MPI send, you had 4. And they had different names and different number of arguments, different types of arguments, different semantics. So that's why it really helped that everything converged to these 2 standards, and also more standards, but these 2. So eager is very useful, say, on latency because you send the envelope and the data together. So you no longer pay 1 latency and then some synchronization and something, and then the other one. At the same time, rendezvous allows you to save that extra copy. Why? Which copy are we talking about? When I send the envelope and the buffer, both are sent to the recipient and they're stored there. But they're not stored in the final buffer, the one that the recipient will pass to MPI receive at some point. That hasn't been issued yet. It will put it directly in this temporary buffer, which means that once MPI receive is called with the final buffer, I will have to copy the data from the temporary buffer to the final one. Which I think there's been a message on the Teams chat. I've seen this notification. I will check it in a second. Which, if you send big messages, a few gigabytes, you don't want these 2 gigabytes to be put on the recipient, assuming there's enough space, to be put on the recipient, and then for that to be copied again to another buffer. In this case, you may want to pay the latency to send another message, but at least you don't have to copy up. So let's see what you did, and we'll do the rest together. Up, like it in here. Okay, so we're sending the count. Oh yes, here. Okay, the current approach is to send the count and then send the date. So somehow this goes away, and we do everything in one send. On the sender, we don't have anything else to do. We just send our message, and that's it. Now, on the receiver, things are a bit different. So how do we do that now? We cannot receive a count because there's no count that has been sent this time. This time there's just been the message. But we cannot receive the message directly because we don't know the count yet. So instead we must retrieve it in a different way. And the different way is to have a look at the envelope. And how do we have a look at the message envelope? Yes, we're going to probe it. Probe, in this case, just means checking something without receiving the message. So the probe is the rank that we're looking for. So who sent the message that we're looking for? What's the rank of that MPI process? Here. Yes. What's the tag of the message we would like to probe?
My_rank. Did you do that one already?
Where, sorry?
Where is that, Lorenzo?
So which part?
My_rank.
For the tag? Oh, sorry. Oh, from Lorenzo. Sorry. Because I didn't hear Lorenzo. I thought.
Yeah, no, I'm the voice. I'm the voice of the online.
Okay.
Everybody. She's the
Chat.
That's right, the voice of chat.
So if we try Lorenzo, so I guess what you meant was for the first argument. So here, if we try to probe my rank, it means I will try to probe a message that I sent myself. But in this case, what we're looking for is a message that has been sent to us. Indeed, it's to us, but it has been sent by the MPI process 0. So it's not my rank in this case. The tag is 0. We can see it here. That's the tag. That's the source of the recipient, the rank of the recipient. And this is the tag. So 0 and 0. Yeah, let me put some variables. This may be confusing here. So sender rank and tag. Okay. Okay, and we put that in a status object, which I'm going to declare here. Okay, so that is the first part. We obtained the status object for a message that we have not received yet, but just probed. Okay, so now from the status, how do we get the count?
MPI underscore get underscore count.
Yes, indeed. MPI get counts. So we need to pass the status. We need to pass the data type and the count. Oh, all these are. Where's my cursor? Here. All these are pointers, so I need to clear. Okay, that we know it's an MPI int, but it means you could also retrieve the data type without knowing. I didn't make it like that because finding what a data type is quickly becomes complex, so I will not cover this today. But the count is a good old integer, so that we know. So now that we have the count, we can allocate our array and do the receive. Let's see if that works. A probe. Probe. Okay. And remember, since it's a random, oh, but we're in C. So the random value chosen this time for the count was 83. We can print it here to make sure that we're not having a mismatch. The random value chosen is let's try that. Oh, you didn't make anything. Okay. Oh, because I updated my local. Yeah, that's the local version. I think that's the local. That's why. Okay, that's fine. Let's go back to. I don't have a local. Okay, that's fine. Let's connect that. Well, in the meantime, you can try on your own AWS node. By now, I think you had it to work. So, did you manage to get it to work while I just get it back in there? Ah.
Permission is denied.
Right.
Oh, enter the password.
Yeah, it's because I copied the wrong one. That's the right one. Okay, let's up intermediate. Okay, we'll ask for the password again. Oh. Again, why not? I'm not picky. If it keeps asking, I'll keep giving. Oh, source. Oh. Okay, so this time we can go a bit faster. Please go away. Printf values selected. So has anyone managed to compile it and run it themselves? Run it themselves?
See, first in the room or first online?
Let's see if I have enough time to redo it entirely before someone brings the answers. Okay. Too few arguments. Oh. Oh, yes. I think I'm missing the communicator here. Bingo. I need the communicator this way. Okay, and now. Oh, it's not an out, it's in. Okay. Good.
So now the walkthrough.
Sorry?
Now the walkthrough.
Yes, another walkthrough, yes, indeed. So in C, I think in Fortran it's different. In Fortran, every time you run a code with a random number generated, that number is different. But in C, it's not. The C is always the same. So it's 83, so I can run it again and again and again. It'll always be 83. Which, even if you have a random number generated, a randomly generated number, you can still have a deterministic behavior. So you can check that your program is correct. And that was not some luck. Okay. Does that make sense to everybody?
No, can you go through it?
Sorry?
Can
You
you
want to go through? Again? Okay.
Because it looked like you were trying a few things there, which might be helpful for individuals online.
So the first thing I did was to remove the extra send here where we were sending the count. So since the recipient is going to find the count themselves alone, we don't need to send it anymore. So we save the extra send. And we just send the array directly. If we no longer send the count, it means we can no longer receive the count. So instead, before we receive this array, we're going to probe it. Because this MPI send array sends along with the data the envelope, which we're going to check using this MPI probe here. But for that, we need to tell which rank we're after and which tag. There is something I need to check now. We don't need to pass the communicator in probe. It knows the right communicator directly. Oh, look, there's an extra communicator here. Oh, because I'm not, oh, okay. I'm learning from my mistakes because this is the one on my laptop. The one that I said, oh, it's on the right one and to close it. Okay, because the one on the machine is this one, where there's the communicator. So I made a mistake once, and this one, at this time I was finding it weird, like, we don't need to pass the communicator. Okay, I'm learning from mistakes, right? Okay, so we're going to probe, so we're going to check the envelope of the message coming from MPI process 0 with a tag of 0 in the MPI com well. Why did I know something was missing, and I should have clicked the first time? Is because if there's a rank only makes sense in a given communicator. Different communicators, an MPI process may have different ranks. That's why if you give a rank, you need to give the communicator with it. And once we know which message to probe, we're going to store the status obtained into an MPI status object, which we're going to use to then retrieve the count. So we need to explain which data that we're talking about. Because effectively, if you have received 8 bytes of data, it could either be 2 integers of 4 bytes each, or 1 double of 8 bytes. Both are perfectly possible. So that's why you need to say, what is the data type of the message you just received? And once you have called this MPI get count, you do have the count now that you can use to allocate your array and issue the corresponding receipt. Make sense? Online all good? What is the protocol used in this example? Eager or rendezvous? My guess would be eager, because typically the eager limit is set to a few tens of kilobytes and above. Or let's say between 2 kilobytes and 65 kilobytes, that's a common value for eager. So with 4 bytes, we're the textbook definition of eager, because I'm not going to saturate the recipient's memory. If I use, oh, sorry, I was not using 8, I'm using 83 integers. So times 4, that's what? That's 332. So that's not about right. Yeah, no, 332, that's it. 332 bytes. Yeah, that will be eager.